Hello, my name is Jeppe. I'm one of the instructors in AMO physics, and I will be making a video lecture about addition of angular momentum. So, in quantum mechanics, we define angular momentum through the commutation relation that Ji J equals I h bar, and then this Levi-Theta symbol I j k, and then j k. This Levi-Theta symbol is 1 if we have an even permutation that could be x, y, z, and it's -1 if it's an uneven permutation that could be x, z, y, and it is 0 if we don't commute, so we have 2 x's or 2 y's or 2 z's in the 3 indices, then there will be 0. So you all know this from the quantum mechanics, introductory quantum mechanics course. The question is, what do we do if we have to couple a angular momentum? And first of all, we'd like to know, is this also an angular momentum? So we define the total angular momentum J1 plus J2 for 2 individual angular momenta J1 and J2 that fulfills this definition. Of course, 2 different angular momentum will commute. That is J1 I and J2I. So not I in general, just let's say J. So the commutation of one component of the J1 angular momentum operator and one component of the 2 angular momentum component will always be 0. They will always commute, of course. So the funny thing about this is that these 2 conditions, they satisfy that the total angular momentum, that is the sum of the 2, also will be an angular momentum that is fulfill this definition. So that's a good thing, of course. Now when we have established this, then we should know there are 2 choices of bases that we could go for. Either we could make eigenstates of the operators J1 squared, J2 squared, J1z, and the J2z. We'll denote these states J1, J2, M1, and M2. The other choice we have is to go for the eigenstates of the operators J squared, J1 squared, J2 squared, and the combined z component of the angular momentum Jz. So that is J squared, J1 squared, J2 squared, and Jz. The eigenstates of these operators, simultaneous eigenstates of these operators, will be denoted J1, J2, and Jm. So what we like to know is if we have solved in one basis, so we have the eigenstates, let's say, up in the separated basis, then how does this look in the coupled basis, so to speak? The example you should think about here is coupling an electron, its orbital angular momentum with its spin momentum. So that could be, as we saw in the last week's exercise, coupling a spin 1/2 with a spin 1. What does that give? Then we know, also as in the exercise, we know the basis up here, we know the spin-offs, we know the spherical harmonics, and we like to express it in this basis over here. To do so, we will use a general trick in quantum mechanics, and that is using the projection operator. The projection operator of some state alpha looks like this. So it's you're very quick to see that if you come with a ket and act with this operator here, then you get the basis of this state alpha here. So a general trick in quantum mechanics is that the sum of all states in a basis of the projection operator that equals unity. So that doesn't give anything. If you think of matrices, then it will be the identity matrix, one in the diagonal. So we'll do this in this case here. So we can write the state in the JM basis as an expansion by the projection operator identity. So then it will be M1, sum over M1 and M2. And then the projection, so that will be J1, J2, M1, M2. And then the same, bra, J1, J2, M1, M2. And then the original state, J1, J2, Jm. So if you look here, we have the identity. So this is just the one. So actually what we have written here is that J1, J2, Jm equals J1, J2, Jm. That is fairly reasonable. But by introducing this identity operator here, then we have actually made an expansion of the Jm state in the M1, M2 state as a basis. Maybe that's better to call this. The expansion coefficient, which is the important thing here, that is the Klebs-Gordon coefficient here. Klebs-Gordon coefficient. The important thing I want you to take from this video lecture is then when does this Klebs-Gordon coefficient vanish? That is, when are they zero? What condition have to be met for them not to be zero? But that's the most interesting case. So there are two main conditions. The total set component of the angular momentum is conserved. That is m equals m1 plus m2. And the second condition is that the final total angular momentum can have different values between the difference, so J1 minus J2, up to the sum, J1 plus J2. So I would like to substantiate this condition as the final part of this video lecture. So let me make some space over here. And quickly I will take another pen. Yes. So if we start by the first condition, then we will act by this operator Jz minus J1z minus J2z on this state J1, J2, Jm. So this is actually the null operator. So this will be 0. So Jz is J1z plus J2z. And if we then sandwich this expression here with the bra of the other basis, so that will be J1, J2, M1, M2, and then Jz minus J1, Z minus J2, Z, and then J1, J2, Jm. This will of course still be 0. If we act with these over here and this over here, we get M minus M1 minus M2, and then we get the Klebs-Gordon coefficient J1, J2, M1, M2, J1, J2, Jm, equals 0. So what this final expression here tells us is that the Klebs-Gordon coefficient is 0 whenever this is not 0. This is actually what we like to prove, that m equals m1 plus m2. So for the final condition here, I'd like to substantiate, and this is because it's not trivial to prove here. So one way to think about this is to think of the angular momentum as vectors. Of course, if you add two vectors, the final vector can be less than the difference between the vectors or more than the sum of the two vectors. This is sort of hand waving, so instead of just leaving you with that argument, I would like to count the number of states in the two bases to show that the dimensionality is identical. So of course, if we look in the J1, J2, M1, M2 basis, then the number of states, which I will denote n, must equal 2 J1 plus 1 times 2 J2 plus 1. And this is of course because there are 2 J1 plus 1 states of the J1 set operator, and there are 2 J2 plus 1 states of the J2 set operator. If we look in the other bases, the Jn basis, so J1, J2, Jm, then it's a bit more difficult, and we have to rely on the fact that this is true. So we know that we have the final outcomes of the J spans from the difference up to the sum. And we know for each J there will be 2J plus 1 different M states. So now, without loss of generality, I will assume that J1 is larger than J2. And then we have that the total number of states equals the sum from J equals J1 minus J2 up to J1 plus J2 of 2J plus 1. To evaluate a sum like this, I'd like you to look at the proof of the Gauss formula adding up integers from 1 to a final value n. You've probably all seen this formula, but maybe you have not all seen the proof of it. The idea, if you have some numbers, 1, 2, 3, then you take the same and reverse the order, so we have 3, 2, 1, and then you add, so this will be 4 and 4 and 4, and then you have to divide by 2 to get the final value, and the same you can get over here. So we have 1/2, and that's because you have it here, and then you have the upper value, so that will be 2 J1 plus J2 plus 1, and then we have the lower value plus 2 J1 minus J2 plus 1, and then we also have to multiply the steps, number of steps. In this case down here would be 3. In the case over here, then we have the difference between the upper and the lower index, and then plus 1 because we count both the lower and the upper index. And if you do so, you will see that that this difference here, plus 1, it gives you 2J2 plus 1. So I will put this up here, 2J2 plus 1. If you actually calculate this out, then you would get the formula 2J1 plus 1 times 2J2 plus 1, which was what we set out to show. So I know that I haven't proven that this is exactly right. I hope you will accept that this is the case. And I know that Katerina would like to make a video lecture about what the these coefficients really are and how to calculate them. From the setup I have made here, then you have to look them up in some table. That's all for now. Thank you for your attention.